We have a machine that can learn straight minus line rules. It adjusts a few knobs, and predictions get better. But the world is full of patterns that are not straight in any coordinate system we can guess ahead of time. So today we pretend non-minus linearity has never been invented, and we build it from scratch. What it is, why we need it, and the simplest ways to manufacture it. Here is the failure mode from last episode. If your prediction is a weighted sum of inputs, then the decision boundary is a line in 2 dimensions, or a hyperplane in higher dimensions. That is not a limitation of training, it's a limitation of the shape. If the true boundary is curved, no amount of knob turning will make a line become a curve. So we ask a design question. How can we keep the learning machinery, but change the shape family it can represent? The most direct trick is to manufacture new inputs from old ones. Instead of feeding x and y, feed x, y, and also x squared, y squared, and x times y. A straight line in these new coordinates can correspond to a curve back in the original plane. This is not magic. If the score is a weighted sum of x, y, x squared, x, y, and y squared, then the boundary where the score equals 0 is exactly a quadratic curve. The learning problem is still just choosing weights. We did not change the optimizer. We changed the menu of shapes by changing the ingredients we let the model combine. But there is a cost. If you add all polynomial terms up to degree d in n dimensions, the number of features explodes. Even in 2 dimensions, degree 1 gives 2 features, degree 2 gives 5, degree 3 gives 9, and it keeps growing. In higher dimensions, it gets out of hand quickly. We want bendy shapes, but we do not want an uncontrollable number of knobs. There is another way to get curves without inventing a huge list of handcrafted features. Take a linear score and pass it through a non-minus linear function. That single move breaks the straight minus line geometry. Think of it as a soft switch. For very negative inputs, it outputs near 0. For very positive inputs, it outputs near 1. And in the middle, it transitions smoothly. Now combine several of these soft switches. Each one looks at the input through its own line, then turns on or off smoothly. If you add them up, you get a surface that can bend. In 1 dimension, this creates a flexible curve that is piecewise smooth. In 2 dimensions, it creates decision boundaries that are no longer straight lines, but can wiggle to fit structure. Geometrically, each hidden unit draws a soft boundary. One side is mostly off, the other side is mostly on. When you add several of these together, the model can carve out regions by combining half-minus spaces in a smooth way. Watch the decision boundary evolve as we add more hidden units. First, it is almost a line, then it bends, then it can wrap around the center. At this point, we have invented non-minus linearity in 2 distinct ways. 1. Expand the input into many features, then stay linear. 2. Keep the input but insert a non-minus linear function in the middle, then add several such units. The second route is the one that scales. You can add capacity by adding units without enumerating every polynomial interaction by hand. We are not calling it anything fancy yet, but we have the ingredients of the next episode. A layer of units computes many non-minus linear features, learned from data, not handcrafted. Then another weighted sum turns those features into a prediction. Next time, we give this object its name, draw its wiring diagram carefully, and confront the new problem it creates. How do you train all those weights without the learning process falling apart?